also like to acknowledge the land on which we stand, belonging to the Gadigal people of the Youre Nation, and pay my respects to the elders, both past, present and emerging. It's also a pleasure to welcome Yi-Ling. Yi-Ling is an engineer and a researcher. She specialises in applying data science methods to research complex problems, and she worked as an engineer, now bear with me, for the Compact Muons Solenoid, there we go, nearly got there, detector of the Large Hadron Collider at CERN. And her PhD research project concerns the application of machine learning to study the impact of social media communication on public trust and also in science and the scientist. And she's currently a postdoctoral research associate at the Climate Change Research Centre at UNSW as well. So a very accomplished woman. And exciting to have her here this morning. Now, after the talk, there will be a chance to ask questions as well. So if anything comes up that you'd like to have a bit more info on, or anything that you'd like for discussion, make sure you hold on to those things, and we'll have a roving mic at the end as well. So please join me in welcoming Yi-Ling.
Can anyone not hear me? It's working? Okay. So I'm Yi-Ling, or you can call me Ling, as my friends and family call me. So when Daniela sent over the title of the talk, how do we begin to understand the origins of the universe? I thought to myself, this sounds really interesting. I would like to hear this talk. And then, oh wait, I have to give this talk. So it's quite a daunting task to be talking about such an immense topic. So I decided I'm going to narrow it down a little bit from an engineer's perspective, because I'm an engineer. I'm going to be talking mainly about the Large Hadron Collider experiment at CERN, how it works and the engineering aspect of it. But before I go into that, I would like to share with you a little bit about myself, where I come from, and how I ended up working at CERN, just to give you a bit of context and background. And also a disclaimer, as Daniela mentioned, I no longer work at CERN. I'm now a postdoctoral researcher at the Climate Change Research Centre at UNSW. So this talk is about my life once upon a time ago. So I'm from Malaysia, which is a country in Southeast Asia. It's a tropical country, which means we don't have 4 seasons. The only season I ever experienced growing up was summer. And in fact, before I went to Europe, the lowest temperature I ever experienced was 27 degrees Celsius. So one of the most interesting things about Malaysia is we have some very advanced technology. For example, this is the Petronas Twin Towers, which until 2004 was the tallest building in the world. But most of the country is still covered in vast tropical rainforests. And many people still live in rural villages such as this one. So we might not have the most advanced technology, the fastest train, or the fastest internet, but what we do not lack is a clear, beautiful night sky. One of my fondest childhood memories is these long walks we used to take in the big rice field close to where we used to live. And like any child, I was curious about the world and the universe. And I remember once staring into the starry night sky and asking my dad, who owns the stars? And my dad told me, the sky and the stars belong to everyone. As a precocious kid who was just starting to get the concept of owning things in this capitalistic world, I remember feeling quite amazed by this fact. And it just kind of stuck with me ever since. And I remember thinking to myself at that time, wouldn't it be so cool if someday I can build something to discover the secrets of the universe? Fast forward 10 years later, I graduated from high school and I got a scholarship to study engineering in Germany. So I packed my bags and took a 13-hour flight and landed in Karlsruhe in the southwest of Germany. And that was quite an eye-opener. I had to learn a new language, and everything was different. People, culture, food, the weather, everything. And my time in Germany was some of the most challenging, but yet educational years of my life. I majored in power engineering. So that is the study of power or energy generation using all sorts of means. But at the back of my head, I think I never forgot my childhood dream of someday building something to discover the secrets of the universe. When I was in the last year of my uni, I stumbled on this job advertisement from CERN, advertising for one of the technical student positions. For those of you who don't know, CERN is the French acronym for the European Organization for Nuclear Research. I didn't know anything about particle physics at that point, but I vaguely knew a little bit about what CERN does, and that was enough to awaken this dormant dream of mine to someday study the universe. But I also knew that Malaysia wasn't a member state of CERN, so my chances of getting in were very, very slim. But I applied anyway. I was rejected 3 times. But eventually, and very fortunately, I got in. And that completely changed my life. So what is CERN? What does it do? CERN is the biggest physics research organization in the world, and it is located in Geneva, Switzerland. It was founded in 1954 by 12 Western European countries. So it was founded 9 years after the end of the Second World War. And at that time, science, and in particular particle physics, didn't have the best reputation. It was associated with industry and weapons, thanks to the atomic bomb. So this group of scientists wanted to come together and create a research organization to prove to the world that science and particle physics can be used as a means to build peace between countries. So that was the founding, that was the philosophy behind the founding of CERN. And that was also the reason why Switzerland was chosen as the venue for CERN, because of its neutrality during the war. And by all accounts, CERN has been very successful in achieving this aim. The Large Hadron Collider collaboration, for example, involves more than 100 countries from around the world, including Germany, France, USA, Japan, Russia. So it is a truly international endeavor. The core mission of CERN is to study particle physics, so to study the fundamental structure of the universe. Now, before we do any kind of scientific investigation, it is important to understand why we are doing it. To ask the question, so what? So why is particle physics important? Why do we want to know more about the fundamental structure of the universe? We know that the world is very diverse. We have different plants, different trees, different people, with different hair color, skin color, heights, etc. But when you zoom into anything in the universe, when you zoom into the smallest constituent of things, you will find that we are all made of the same stuff. Something like this. You might recognize the atomic structure, with the electrons orbiting around a nucleus, which is made of protons and neutrons. A human, for example, is made up of 7 times 10 to the power of 27 atoms. That is 7, followed by 27 zeros. We will later see that some of these elements can be further broken down. But for now, I just want to point out that particles are the building blocks of everything in the universe. You, me, trees, clouds, stars, galaxies, everything. So understanding these building blocks is fundamental to our understanding of the universe and everything in it. And boy, do we have a lot of questions. Why is there something instead of nothing? Why do we have mass? Why is the universe expanding? And so on. So what particle physicists do to try to understand the universe is by looking back in time, all the way back to the Big Bang. We know that the universe started with the Big Bang around 13.8 billion years ago. And immediately after the Big Bang, the universe started to rapidly expand. And during a billionth of a billionth of a billionth of a second, the universe was the size of a grapefruit. And then high energy particles started to form and interact with each other. After a few minutes, the first nuclei were formed. These were the nuclei of lighter elements such as hydrogen, helium, and lithium. The first atoms, so the structure with electrons orbiting around the nucleus, didn't form until around 300,000 years after the Big Bang. And this continues to happen. Matter starts to clump together under its own gravity, forming the first galaxies, and within them, the first stars. And this happened around a few 100 million years after the Big Bang. Our own solar system didn't form until around 9 billion years after the Big Bang. And at around 10 billion years, life on Earth begins. And that is where the biologists come in. For the physicists, the interesting bits are the beginning of the universe, the few seconds after the Big Bang when particles were formed. And what CERN does to study how do you recreate the Big Bang? Now we know that the Big Bang is an astoundingly energetic event. We also know from the laws of conservation of energy that energy cannot be created or destroyed. It can only be transformed into other forms. So all the energy in the universe today was created during the Big Bang. And it was concentrated in this teeny tiny point. So to recreate the conditions of the Big Bang, we need a lot of energy. And then along came this very clever man named Albert Einstein, who, among many, many other things, formulated one of the most famous equations of our time. It is also the only equation mentioned in Stephen Hawking's book, A Brief History of Time. Anyone wants to guess which equation is it? Yes? Very good! There you go, E equals to mc squared. What does E stand for? Not Einstein, I can tell you. Does anyone want to guess? What does E stand for? Energy. Energy. What does M stand for? Close. Stands for mass. And C? Speed of light. Great. You guys are already experts. So I won't go into too much detail, but what this equation tells us is that energy and mass are essentially the same thing. They are like two sides of the same coin. And one can be converted into the other. So energy can be transformed into mass, or stuff, and stuff can be transformed into energy. So the more energy you have, the more stuff you can create. And in particle physics, the stuff that we are interested in creating is, of course, particles. So let's recap. We want to study the beginning of the universe and its building blocks. And to do that, we need a lot of energy. And this energy can then be transformed into mass, or particles, which particle physicists can then study. Now comes the key question. How do you generate this huge amount of energy? Enter the Large Hadron Collider. The Large Hadron Collider, or the LHC, is the largest and most powerful particle accelerator in the world. It is also the biggest and most complex machine ever built by humankind. It is around 27 kilometers long in circumference and spans across two countries, France and Switzerland. And it took around 30 years to build the Large Hadron Collider. Given its size, it would have been really expensive to build the LHC above ground because of the crazy real estate prices in Geneva. So we went underground. The tunnel for the LHC was built around 100 meters underground, and it's around 4 meters wide. One interesting anecdote, when the 27-kilometer long circular tunnel was excavated between Lake Geneva and the Youre mountain range, the two ends met up with only 1 centimeter of error. And because it's so big, the engineers and physicists working on the LHC regularly use bicycles to go around the tunnel. So how does the LHC work? Once you understand the relationship between energy and mass, the way the LHC works is actually pretty simple. The LHC accelerates two beams of protons traveling in opposite directions to almost the speed of light, and then collide them together. And as you might have learned in school, when you collide two things traveling in opposite directions, the total amount of energy resulting from this collision is the sum of the energy of the individual colliding thing. In the LHC, each proton traveling at almost the speed of light carries an energy of 7 tera-electron-volts, 7 TeV, that is a unit for energy. So when two protons collide, the total amount of energy is 7 plus 7, 14 TeV. So to put things in perspective, 1 TeV is roughly equivalent to the energy of a flying mosquito. So when you think about it, 14 TeV doesn't sound like a lot, does it? But in the LHC, this energy is squeezed into an extremely small space, about a million times smaller than a mosquito. And it is this energy concentration that makes these collisions so powerful. When you clap your hands, you're probably creating collisions with energy that is higher than the proton collisions in the LHC. But the energy is much less concentrated. But now imagine if you put a needle in the middle of your hand. You will probably clap much slower and softer because it's going to hurt. And it is precisely this concentration or intensity of the collisions that cause the protons in the LHC to be smashed apart. Now, each proton collision in the LHC generates an energy of 14 TeV. But in the LHC, there are trillions of protons. So the total amount of energy resulting from these collisions is around 360 megajoule. And that is enough energy to power a small city, and all concentrated in this teeny tiny point. The result of these collisions are a barrage of other subatomic particles, which are then captured by detectors and studied by particle physicists to answer the questions we have about the universe. So the acceleration in the LHC actually happens in stages. The source of the protons is a simple bottle of hydrogen gas, and an electric field is applied to strip the hydrogen atoms of their electrons, leaving behind the protons. The protons are then injected into the linear accelerator tube, where they are accelerated to around 1/3 the speed of light. And then the protons are injected into the proton synchrotron booster, where they are accelerated to 91% the speed of light. And then in the third stage, the protons are injected into the proton synchrotron, which has a circumference of 630 meters. And the protons circulate here for around 1.2 seconds, reaching a speed of 99.9% the speed of light. And then the protons are injected into the super proton synchrotron, which has a circumference of 7 kilometers, and they continue to be accelerated. And soon, the packets of protons are sufficiently energized to be launched into the gigantic Large Hadron Collider. The LHC continues to add energy to the protons, and now the protons are traveling so close to the speed of light that they go around the 27-kilometer long tunnel 11,000 times every second. And finally, each proton carries an energy of 7 TeV, and it is now 7,000 times heavier than it was at rest. And now the protons are ready to collide. The collisions of the protons happen at 4 crossing points along the LHC, which are built with giant detectors to capture these collisions. Now I have an animation to show this process, but I hope it works. Yeah. So starting in the booster, the protons are then injected into the proton synchrotron, and then into the super proton synchrotron, and finally into the Large Hadron Collider. And then the two beams of the protons meet up in the detector, smash into each other, and resulting in a rainfall of other particles. Okay, so the LHC is big and powerful and does all sorts of amazing things. But it is actually quite useless if not for the detectors that are built at the crossing points of the beams where the collisions actually happen. This is the Atlas detector. It is the biggest detector of the LHC, And just to give you an idea of the size, if you look closely, there's a man standing right here. So the Atlas detector is around 46 meters long, 25 meters wide, and weighs around 7,000 tons. And the LHC has 4 of these cathedral-sized detectors built at the crossing points of the beams. Atlas and CMS, they are the 2 general-purpose detectors, with Atlas being the bigger one, and CMS the heavier one. CMS is almost twice as heavy as Atlas, and that is almost twice as heavy as the Eiffel Tower. And I was part of the CMS experiment. And then we have the LHCb detector, which specializes in detecting heavy particles containing a certain type of element called the bottom quark. And finally, the Alice detector, which is designed to study heavy ion collisions. As an analogy, these big detectors are like giant cameras taking pictures of the collisions. And the result of these collisions is a myriad of other exotic subatomic particles, each with its own unique trace or track. And it is this debris of the collisions that particle physicists are actually interested in. So how does the debris of the collisions look like? I mentioned before, we are all made of particles. And there are many different kinds of particles in the world. We used to think that an atom is the smallest unit of matter. In fact, the word atom actually comes from the Greek word atom, which means that which cannot be split. But of course, we later realized that this is not true. An atom is made of other particles, namely electrons, protons, and neutrons. And as science progressed and we gained more knowledge of the structure of an atom, we learned that protons and neutrons are made of even smaller particles, namely quarks. Proton is made up of 2 up quarks and 1 down quark, and a neutron, 2 down quarks and 1 up quark. And quark, as we shall see, is what we call an elementary particle, meaning it is truly the smallest unit of matter and cannot be broken down anymore. Scientists have discovered quite a few of these elementary particles, and they are the basic building blocks of everything in the universe. So it's kind of like building the Lego models. Any one of you played with Lego models before? Yeah. Yes. It's really fun. So this is a model of the CMS detector, made entirely from Lego bricks. What this represents is stuff in the universe. Things, you, me, tables, chairs, everything. And this model is made up of individual Lego blocks. And these Lego blocks represent our elementary particles. They are the basic building blocks that you can use to build other things in the universe. So all these elementary particles and the forces that govern them are very elegantly described in what we call the Standard Model. The Standard Model is the closest candidate we have for the theory of everything. It was developed in the 1970s, and it has so far very successfully explained almost all experimental results in particle physics, and also very precisely predicted a wide range of phenomena. And as science will tell you, those are 2 very important features of a good theory. Now, the next few minutes of my talk is going to be a little bit heavy on particle physics, but please bear with me. I promise you it's going somewhere interesting. So, I would like you to look at the red particles over here. These are what we call force carrier particles. And it is the exchange or interaction of these particles that creates 3 of the 4 fundamental forces in our universe, such as the electromagnetic force, which is carried by photons. And then we have the strong force, which is carried by gluons. And it is the strong force is what binds protons and neutrons together to form the nucleus of an atom. And then we have the W and Z bosons, which carry the weak force. And the weak force is responsible for radioactive decay, and is important in nuclear fissions. The W and Z bosons were actually discovered at CERN by a physicist called Carlo Rubbia, and he won a Nobel Prize in Physics for this discovery. Anyway, these force carrier particles, these red particles, are what we call bosons. And up until 2012, one very important component of the standard model was missing. And that is the Higgs boson. The Higgs boson is like the biggest missing puzzle in the standard model. It's like the holy grail of particle physics. It was hypothesized to exist by the standard model, but experiments have so far failed to find it. So what is the Higgs boson, and why is it such a big deal? Put very simply, the Higgs boson is the particle that gives everything in the universe their mass. And you can think of mass as the quantity of matter. So without mass, nothing would exist, as we are all made of matter. And that is why the Higgs boson is so important. It gives everything mass, and it's the reason why we're all here. And for this reason, it has been called the God particle by the media, although that's also controversial. One of the most important tasks of the LHC is to find the Higgs boson. The Higgs boson actually got its name from Professor Peter Higgs, who is a particle physicist from Scotland. Professor Higgs, with a few of his colleagues, developed a theory for the Higgs boson back in 1964. But back then, technology wasn't advanced enough yet for them to test their theory. So for almost 50 years, nobody actually knew if the Higgs boson existed or it is just a theory. And it wasn't until 2008, when the LHC was completed, that we can finally test this very important theory. And guess what? We found the Higgs boson. In July 2012, CERN announced that the Higgs boson was independently, and this is very important, discovered by both the ATLAS and the CMS detectors. And I remember that as one of the most exhilarating days of my life. Professor Higgs was in the theater hall where the announcement was made, and cameras actually caught him wiping away tears. 50 years of work, finally validated. And the following year, 2013, Professor Higgs and Professor Englert were jointly awarded the Nobel Prize in Physics for their formulation of the theory of the Higgs boson. And Professor Higgs was 84 years old that year. So that was a very happy moment for me to have been part of an experiment, the CMS experiment, that made the discovery possible. And in a way, my childhood dream of someday building something to discover the secrets of the universe did eventually come true. So that was a lot of spotlight on the physicists. Now, what about the engineers? What did we do? We know that a scientific breakthrough can only be achieved when a theory has been experimentally validated. So the theory part is the job of the physicists. They develop theories based on existing knowledge and observations. But a theory remains just that, a theory. It isn't until engineers build things that physicists can then use to test their theories that a theory can become proven. Just like the story of the Higgs boson. Professor Higgs and his colleagues developed the theory of the Higgs boson back in 1970s. But back then, technology was not able to test his theory. The energy that is required to produce a Higgs boson was simply too high. So it wasn't until technology and engineering had caught up with their theory that we can finally carry out experiments to validate their predictions. So it's kind of like a symbiotic relationship. Physicists need engineers the same way engineers need physicists. At CERN, the LHC engineers work on a wide variety of things, but they can roughly be grouped into 4 main categories. They build things to accelerate the particles, to steer the particles, to isolate the particles, and to investigate the result of the collisions of the particles. For the 5 years that I worked at CERN, I was involved in 2 of these 4 tasks. So first up, accelerating the particles, namely almost the most important task of the LHC. This is done using radio frequency cavities. So these are metallic chambers that contain an electromagnetic field. So when charged particles, such as protons, enter these chambers, they are acted upon by a force of the electromagnetic field. These radio frequency cavities are structured like beads on a string. The beads are the chambers, and the string is the beam pipe through which the particles travel. And these chambers these cavities are connected to a radio frequency power source, thus generating an electromagnetic field. And protons that are positively charged are injected into the beam pipes. And as the protons approach the first cavity is switched to become negatively charged. And as we know, opposites attract. So now the protons are pulled into the first cavity. And as soon as they enter the first cavity is switched to become positively charged. And as we also know, things of the same charge repulse each other. So now the protons are pushed away from the first cavity and towards the second cavity, which is now switched to become negatively charged, and it pulls the protons into it. So this is done over and over again at a frequency of 400 megahertz. So that is 400 million switches every second. And that is how the protons are accelerated to almost the speed of light. Moving on to the second important engineering task, steering and focusing the protons. Now, as the protons are traveling faster and faster, the force that is needed to steer them and keep them in the circular beam pipes also gets bigger. Imagine, for example, you're swinging a big iron ball with a string attached to it. The faster you swing the ball, the harder you will feel the ball pulling on the string. And that is the centripetal force, and that is exactly what is happening in the LHC. And not only that, the protons are also approaching the speed of light. And we know that nothing can travel faster than the speed of light. So once the protons come very, very close to the speed of light, any energy that is added to the protons now, instead of making them go faster, it actually makes them heavier. So the protons actually gain weight as they are being accelerated. Imagine, for example, a big and heavy truck that is traveling very fast. It will be so much harder to steer this truck compared to, say, a bicycle that is much lighter. So to do this, the LHC engineers use a technique called cryogenics, which is a branch of physics that deals with very, very low temperatures. The LHC is actually the biggest refrigerator in the world. The magnets that are used to cool the coolant, that is the magnets that are used to steer and focus the protons, are cooled to a temperature of minus 271.3 degrees Celsius. That is even colder than minus 270 degrees Celsius of outer space. So you can quite literally say that CERN is the coolest place on Earth. And this is a picture of the LHC magnet. And there are around 10,000 of these magnets lying around the LHC tunnel. Now, why do we need the magnets to be so cold? To understand that, we need to understand a concept called superconductivity. Superconductivity is a phenomenon whereby the electrical resistance of some types of material, when cooled below a certain temperature, called its critical temperature, becomes exactly zero. In other words, the material becomes superconducting, and electrical current can just flow through it with no resistance at all. So when there is no resistance, you can have higher amount of current flowing through the material or the wire. And we also know that the strength of the magnetic field is proportional to the amount of current flowing through a wire. So more current, stronger magnetic force to bend and focus the protons. And that is why we need the magnets to be so cold. The coolant that is used to cool the magnets is liquid helium. And one of the projects that I worked on when I was at CERN is to design a control system to control the supply of liquid helium to the LHC magnets. Now the amount of current that is needed to generate this strong magnetic force to steer and focus the particles is around 11.8 thousand amperes. Just to give you an idea, a current of 0.1 ampere is enough to kill you. And the current in a lightning is usually around a few thousand amperes. So 11.8 thousand ampere is a lot. And that is why we need superconducting magnets. This is a picture of the inside of the magnets and the technician working on it. Another interesting thing about the LHC magnets that I would like to share with you is the idea of precision. The proton beams in the LHC have a diameter of around 16 microns. That is around a tenth of the size of an average human hair. So as you can imagine, colliding two things that are super tiny and traveling super fast is super hard. So the task of focusing and colliding the protons in the LHC is akin to firing two needles from 42 kilometers apart and having them collide exactly halfway. Very difficult, but not impossible. The third thing that LHC engineers need to make sure of is to isolate the particles. And they do this by building a big vacuum system in the LHC. Now the reason we need vacuum in the beam pipes is pretty simple. As the protons are accelerating along the beam pipes, we don't want them to collide with other gas particles, as this would make them lose energy. So we try to suck out all these gas molecules as much as possible. The vacuum in the LHC is as empty as outer space. And the system that is used to create this vacuum using very powerful pumps is one of the biggest in the world. Finally, the fourth engineering task, computing and software. So for 3 of the 5 years I worked at CERN, I worked on the detector control system of the CMS detector. Basically, I was designing software to configure, monitor, read out, and control the various parts of the detector, including cooling, low voltage, high voltage, vacuum, etc. So these various subsystems have to work seamlessly together for the detector to function properly. So it's quite a challenging task. The second important function of the CERN computing infrastructure is to record, store, and process the results of the collisions in the detectors. So the collisions are recorded as electrical signals by the chips or the cameras of the detectors. And this data is then sent to the CERN data center to be processed. The LHC generates around 40 million collisions every second. And these are all data points that have to be captured and processed somehow. This is a huge amount of data, and it is quite a monumental task to actually store and process them. This huge amount of data is stored in servers in the CERN data center, and the computing power that is needed to crunch this data is so big that CERN cannot handle it alone. So the task is actually shared with computing centers around the world through the worldwide LHC computing grid. And even then, CERN still processes around 1 petabyte of data every single day. That is 1 followed by 15 zeros. And it's roughly equivalent to 210,000 DVDs full of data every single day. So we have seen all the important components of the LHC and how they must work together for the LHC to run smoothly. How does that change your idea of how a scientist looks like, or what a scientist does? We used to think of scientists of this eccentric, white male who sits alone in his desk and works in isolation all day long. But what the LHC has shown us is that this idea is so profoundly false. And this brings me to the final element of the LHC that I would like to talk about, and that is people. Nothing would work at CERN without a collaboration between people from around the world with different expertise, knowledge, and backgrounds. This is a picture of the CERN Control Center. And during the startup of the LHC, it looks very much like the NASA control room during the launch of a spaceship. And when you think about it, the startup of the LHC bears many similarities with the launch of a spaceship. They are both the result of many years of hard work, incredible engineering ingenuity, and also active collaboration between people with very different ideas and backgrounds. And because the machines are so complex and so expensive, you only get one chance to get it right. Otherwise, it will be a very expensive mistake. There are more than 10,000 people working at CERN, coming from more than 100 countries. So it's kind of like a mini United Nations, really. This is a picture of the CERN summer students. They're basically university students from around the world who come and spend a summer at CERN working on different projects. They are a fun and vibrant bunch, and many veteran scientists at CERN actually started out as summer students. Of course, there are also more experienced physicists and engineers. They all have very different backgrounds, but they are all brilliant, passionate, and hardworking people. There are people from countries that are leaders of the world in science and technology, such as Germany, Australia, France, USA. But there are also people like me, who is from a developing country. And you don't even have to move to Europe to work for CERN. There are institutes and universities in Australia that are partners of CERN, and you can work there. Working at CERN has changed my life and my worldview. If you ever think that science and engineering is a boring career path, I can assure you it is not. It's quite the opposite, actually. My research at CERN has brought me to many new places in the world and met many interesting people. I have taught in schools, presented at conferences, learned from experts, and even played in a CERN rock band. So science rocks. So before I wrap up, I would just like to share with you a little personal story and a parting message. Let's see. This is a picture of my desk back home in Malaysia up until I was around 18. Notice the absence of any form of electronic devices. In fact, I didn't own a mobile phone or have internet access until I went to study in Germany. Fast forward 15 years later, just a few days ago, I was chatting with my parents and my brother. I was in Sydney, my brother in China, and my parents in Malaysia. And we were on 3 different devices and 2 different chat programs because Google Hangout doesn't work in China. And it suddenly hit me how much the world has changed and how much this change is contributed by progress in science and technology. I mentioned in the beginning of my talk the conversation between my dad and I when I was a kid, and my dad told me the sky and the stars belong to all of us. I would like to add, so is knowledge, and our amazing ability to ask interesting questions and to understand the universe. In the words of Carl Sagan, we are a way of the cosmos to know itself. So my parting knowledge to all of you is, while technology has immensely changed and improved our lives, we should never forget the power of simple curiosity, wonder, and imagination. The LHC is a result of pure human curiosity. Sure, there were eventually spin-off technologies that came out of experiments, but they were not the goal of the LHC at all. We just wanted to know how the universe works. And that, to me, is the manifestation of the best of humanity, this spirit of questioning and collaboration. So maybe, sometimes it's not a bad thing to just pause, put down your phone, and talk to your friends. And if you're lucky, under a starry night sky. So keep looking up.
Thank you, Yi-Ling. That was amazing. And I'm sure you have lots of thoughts and questions bubbling away. So if you do, pop your hand up. So many hands. Pop your hand up and I'll get around with the roving mic.
Thank you. 2 questions, if I may. First, with quarks, whatever happened to truth and beauty?
That's a great question. I know, so I guess I know why you asked the question, so many sides. Because we have up, down, charm, strange, you can see, they have names for all these different quarks. What happened to truth and beauty? That's a great name. I don't know. Yeah, maybe we'll discover new quarks in the future. We'll name it truth and beauty.
Back in the 80s,
yeah.
one of the family, one of the pairs was actually called truth.
Oh, so you are a particle physicist.
No,
I should shut up.
I worked for a science program. So.
Ah, okay.
Yeah.
That's good to know. I didn't know that.
Yeah.
So truth and beauty used to be one of the
Yes.
family. Okay, thank you.
They got lost somewhere, didn't they?
Yeah, they did. It's a pity.
And the second one is the quote you made about scientists and engineers,
Yeah.
I kind of feel that it should be reversed.
Oh,
Because
okay.
without a scientist thinking up what could be possible, how is an engineer going to create something that makes it observable?
Mm. So you need to imagine something is possible before the engineers can actually create them. What was the quote? This one discovers that which exists. Ah, okay. Right. Yeah, I guess the word
It's
discover.
the verb.
Yeah.
One should be creates, the other is makes.
But do you think scientists create things, or they discover things that are already there?
They think things up.
Yeah.
Yeah. I mean, science is all based on theory. If you don't
That's
have
true.
a theory to test, then you can't test it.
Yeah, but the theory, the goal of the theory is to discover things that are already there.
Sure.
I think.
But you
Yeah.
still-
Yeah, exactly. You can interpret it the other way around as well.
Thank you.
Yeah, thank you.
Okay, just go to this gentleman in the blue shirt.
Thank you. The talk was fantastic. Two questions as well. One, why on the physicist language they don't use anymore matter or mass, but rather stuff? And the other one is, okay, everyone says that everything started with the Big Bang, but nothing comes from nothing. So what is before that, and what created? Please don't say St. Augustine, because we know that he said that was God that was creating hell for people who ask this question.
Yeah, I just wanted to say that.
Do we have all day? Maybe.
Those are two excellent questions. So the first one, why do we call matter stuff? That is just a word I use. I apologize if it's not a. I just wanted to use a word for you to imagine things that you can touch. Matter, because force is another kind of particles, which is very hard to imagine. But I want to separate those two. Matter or stuff are things that are concrete that you can touch in the universe that are observable. But stuff is just a colloquial word. So the proper word is matter. The second question, what comes before the Big Bang? The only responsible answer I can think of is I don't know. Because I truly don't. And there are a lot of theories on how the Big Bang began, but they have never been tested and proven, so they are just theories. One of the theories is quantum fluctuation. Things can come out of nowhere. It just fluctuates. It comes out and then it disappears. It comes out and it disappears. But we don't know how, and we cannot prove it yet so
So
far.
the Big Bang is only the frame of time from now,
Yeah.
where the science.
Exactly, that we can observe so far. Yeah.
That where we are in scientific language land, like the Big Bang as the last.
Yes, the Big Bang is when everything begins. Exactly. Yeah. And the reason we think that the universe started from this teeny tiny point is because we know that right now the universe is expanding. And it's expanding at an accelerating speed. That means it's expanding faster and faster. So if you think back, if it is expanding, that means at a certain point in the past, it was really, really tiny. And that is how the scientists thought, oh, okay, if it is expanding, in the past it must be really tiny. And they go all the way back to this Big Bang theory.
Couldn't that be argued that that's only from one point of view, because that's a condition that we are,
Yeah,
that's just.
that is one point of view that is very well supported by experimental results as well. Yeah, there are multiple independent investigations that all arrive at the same conclusion.
I really enjoyed your talk. It was great.
Thank you.
But I just want to
Glad.
point out that in case anybody thinks this stuff is esoteric and doesn't affect them, that MRI scans depend on exactly the science that you talked about.
Yes.
Superconducting magnet, very cold
Exactly.
temperatures using helium, and affecting the spin of electrons
Yeah,
in our bodies.
you're exactly right. A lot of the applications that we use that are useful are actually a result of these fundamental research. Things that started out just as a question. Where did we come from? What is the universe doing here? I think you had a question?
Do we know if there are other universes?
Great question.
Multiverse?
Multiverse. I knew this question was going to come up.
Parallelverse?
Yeah. Okay. So the question of multiverse is because there is this thing called the cosmological constant. And it is a random number that is in the equation of the universe. Let's call this A plus B equals to C. And you need this cosmological constant, that is X, let's say, in order for this equation to work. But this is a cosmological constant, which is discovered by, of course, Albert Einstein, is a very random number. And it is very, very precise. It is 10 to the power of minus 120. So it's 0.000000000. It was very precise. And if it is off by a tiny amount, we wouldn't exist. The universe won't be here. So scientists are very uncomfortable with this idea. How can things be so random, like so precise? So the theory of multiverse comes from that. It says that there are actually many different universes with many different values of this constant. And they just couldn't form because the laws of physics are not right. That's the only logical explanation. But it hasn't been proven, and I don't know if we can prove it. Multiverse, it's a theory.
So if the universe is expanding, do we know where the boundary is?
We don't know. Yeah, we don't. We don't. Because it's expanding at an accelerating speed, and into what? We don't even know. And also, we don't even know if the edge of the universe that we can see is actually the edge, because we can only see things as far as light goes, because nothing travels faster than the speed of light. And the furthest we can see was 13.8 billion years. Maybe further beyond that, there are still things, but the light just hasn't come to us yet. We don't know. So, yeah, there are so many questions that we still don't know. And
So
yeah, that's a
we
good
can't
question.
really see in the black hole.
Oh, the black hole.
Sucks in.
Yeah, would you like to answer the question? Why can't we see in a black hole?
Because, well, it really depends on what it's sucking in. Like, if it's like a sun, we might be able to see the sun just disappear like that. Then we might be able to see like a tiny slither of the black hole. Maybe, I'm just thinking.
Yeah, no, thinking out loud is good, and you're very close actually. You cannot see a black hole because we see things through light, and the black hole sucks in everything. You say it sucks in everything, so you can't actually see anything. But you can observe the effects of the black hole because it's so massive. So the gravitational pull of a black hole is really, really big. So, and we know that if something is really heavy, really massive, things might revolve around it. We revolve around the sun, for example. And if you see a planet revolving around nothing, you might think, oh, maybe there is a black hole there. That is how we infer the existence of black holes.
What's the black hole? It's a star that collapses.
Yes.
Yeah.
One of the ways black holes form is the collapse of very, very big star. Just collapse into this tiny, tiny point that is super massive. That all the mass of the star, imagine the whole universe, the whole solar system suddenly collapse into this tiny point. So it's super dense, it's super heavy. That's why it has this strong gravitational pull. Yes?
Can you explain dark matter without?
You're very clever. You are very clever. That's a good question. Let me see. Maybe I have a slide somewhere. Yes, dark matter, dark energy. So everything that I have talked about for the last hour only makes up 4% of the universe. Everything that we have discovered. The rest, and scientists are very good in coming up with names. We don't know what they are, we will call them dark energy and dark matter. That is how it is. The Big Bang, it's big and it's a bang, so it's a Big Bang. So we are really good in that. So the dark matter is, we call it dark matter because we essentially don't know what they are. But like a black hole, we can observe their effect. We realize that if there is no dark matter, some stars will spin away from each other. But they don't. They seem to spin around things that we cannot see. So we infer that there is something there, but we don't know what they are. So we call them dark matter. And dark energy is actually the thing that is making our universe expand. That is the dark energy. We also don't know what they are, and they make up 74% of the universe. the theory that particle physicists have now is that dark energy and dark matter are made up of unknown particles. Like the Higgs Boson, it wasn't known before. There might be other particles that we don't know, and they made up this dark energy and dark matter. Does that answer your question? Yeah? It's a great question.
Okay, we have time for one more question.
Yes?
Are we now, with the understanding of animals and other things in the environment from the human perspective only, worth understanding from their perspective how, do you know what I mean? Like, they might have the answer to more answers, to more questions that human asks.
Like other...
Like, imagine if a whale that we had perceived it, like, because we only have so much money dedicated to study probability, that they might have much more knowledge, or do we know everything about the animal kingdom, basically?
We don't, yeah. We know very, very little about animals. Yeah.
Like, if I was like a billionaire, I think that was my first
Yeah. I know, yeah. Yeah, exactly. And it's very hard to understand what other beings think. We can't even know what you are thinking. I don't know what you're thinking. So it's even harder to understand what whales think if they can't actually verbalize that, for example. Yeah. So maybe...
Our perception that they have a lack of connection to the language that we
Yeah.
work.
Yeah, we understand them from our perspectives. So it's very limited. Yeah.
Okay, well, please join me in thanking Yi-Ling again. What a gift she has in just communicating such complex things so clearly. Yeah, I found it very interesting. I'm sure everyone else did too. We do have a whole host of other events across our 3 libraries here at